Okay, in this video we're going to look at waves, and we're going to look at stationary waves in specific. So we're going to look at how a stationary wave is formed, and we're going to look at the kinds of where we can see stationary waves in effectively 3 different situations, and we're going to look at the kind of bits and bobs to do with that as well. Okay, so we start out with what is a stationary wave. Well, a stationary wave can be set up on a string more often than not, where we have a vibration generator and we have a string which effectively sends a wave down to a fixed end of usually on a pulley of some description with masses attached. And we're probably going to show this in lesson. And effectively what you get as a result of that is a standing or stationary wave that looks something like this. Now the point in this is that you can, this is caused by superposition. Now, how do we suggest how this is caused? Well, we suggest that the wave is propagated from the oscillator, from the source down towards the fixed end. So the wave travels down the string, okay, or could be in an air column or something that we'll talk about later on, and it reflects off the boundary. Okay, this is the boundary right here, so the wave reflects off that boundary and travels back the way. So the effect of that reflecting means that the 2 waves, the wave that was going and the wave that is now coming back, superpose upon each other. So superposition of original and reflected occurs. So the superposition of the original and the reflected wave occurs, and as a result we get what we like to suggest as nodes and antinodes created all the way along. Now the points where you see no movement is called a node for node movement. Node movement. There's no movement whatsoever. Okay? Effectively that is caused by destructive interference, as you would expect. Effectively, the wave in this direction was doing that, and the wave in this direction was doing that, and as a result, we get no movement, i.e. the particles aren't oscillating. Retrospectively, we get something called an antinode. An antinode is an anti-no movement, so anti-node. So a place of maximum displacement, of maximum amplitude, okay? We've got antinode there, antinode there, antinode there, antinode there. Positions of maximum amplitude. They are caused by constructive interference. Obviously, what we'd expect to suggest about that one is that when we've got the reflected wave is like that, and the incident wave, the initial wave, is also like that, and so we get our constructive interference, which is the combination of the 2. And bear in mind this happens at all points along the wave, so you're getting variations on constructive and destructive interference up until a maximum constructive, and then that drops off until it's maximally destructive, and so on and so forth throughout the wave. So these 3 points are your standard response to how a stationary wave is set up. It travels down the medium or down the string, reflects off the boundary, the superposition of the original reflective wave create nodes and antinodes through constructive and destructive interference. So, more about these stationary waves then. So, obviously, depending on the length of the spring and how fast this is vibrated, i.e. the frequency, depends on what you get produced here. Now, the most fundamental simple wave that you can get has to be, I'll do this in black, has to be that. So effectively what we're getting there is we're getting constructive interference all the way along. The wave is being vibrated down but then reflects, and the effect of that reflection is that we get an antinode here and two nodes at the ends of our string and at the boundary. Same rule applies. Wave is transferred along the string, reflects off the boundary, superposes with the original wave, and creates constructive and destructive interference along its length. And obviously as we increase the frequency we can get different values, but this is otherwise known as the fundamental. Okay, we can't get anything simpler on a string. It's the fundamental mode. Okay, we can't get anything simpler. Obviously, as we increase, we can go to something like this. Okay, where you've got a full wave in that incident. And obviously we can keep going up and up and up and up until we get to very, very high proportions of the length of the, again, loads of waves on there. As we've already seen, you might get something that looks like that, okay, on the string. So we get this situation occurring. Now, interestingly enough, there are some features of stationary waves you need to be aware of. Now, stationary waves share some properties with progressive waves, but effectively, instead of transferring energy like a progressive wave was, so like a progressive wave transfers energy in that direction, depending on, obviously, the oscillations that depend on whether it's transverse or longitudinal, but for a standing wave, there is no net energy transfer. So where does that energy go? Well, it's stored. The energy is stored in the antinodes. You've got an amount of energy that's stored in those antinodes. So instead of being transferred along, we're storing that energy in the antinodes. And actually what's quite nice about that is that if I was to grab a node and stop it from vibrating, well, nothing would happen. I wouldn't be quelching that energy at all. Whereas if I grabbed an antinode, then it's going to kill the wave, and I'll show you that in lesson. So we're storing energy in the antinodes of the wave, the standing wave. What's interesting to consider now is phases as well. Whereas particles along a progressive wave compared with particles in a standing wave do something very, very different. Effectively, in a progressive wave, we look at, okay, well, we'll look at the point there, and we'll look at a point there, and we'll go, okay, right, well, that's 90 degrees, that's 180 degrees, so they're 90 degrees out of phase with each other on those oscillations. And that's effectively the phase difference that we're talking about there. But what about in a progressive wave? Well, think about what's happening here. At any point along this wave, they're all moving up or they're all moving down at the same rate. It is not progressive, okay? It's stationary. All of these particles are moving down at the same way all the particles are moving up at the same time. So effectively in this situation, if you have any particle, if you have 2 points on this wave, let's call that one A and we'll call that one B, then you might think, oh, like a progressive wave, we need to find the angle there and the angle there. No, you don't. Effectively, because they're on the same portion of the wave, i.e. they're between two nodes, that's an important point, between two nodes, they are constantly in phase. The particles here and the particles here are moving upwards at the same time, and they're moving downwards at the same time. Obviously, if we relate that to particles at this point along a wave, so if we compare a particle here, so C and B, then C and B are what we call antiphase. As you would imagine, these are about to move up, these are about to move down, so they're going to be moving like that all the time. They're always going to be in antiphase. So, particles are always in phase or in antiphase. There can be no difference, okay? There can be no difference. They're always either in the same phase or they are in antiphase because of the nature of the stationary wave and the particles. Obviously, you know that's not the same case for a progressive wave. Okay, so other features of important information that you need to be aware of is that we can also set up waves in air columns, which makes sense because obviously air is a sound wave and it bounces, reflects and superimposes like all of the waves do. So if we have a sound column here with a fixed closed end at one point, we can set up a fundamental. And the fundamental for an open air column looks like that. Now that portion of the standing wave is basically the same as, if I draw both parts this way, it's basically that part of the stationary wave in the air column. So effectively that's quarter lambda. And we can set up waves similar to that with variations where the node is at the end and we have an antinode at the open end. So we've got that there, and obviously we're going to end with it like that, so we can do something like that. And we can keep going. We can keep going like that. So that's 3/4 lambda. Okay, because we've not got a full lambda there just yet. Remember, that's a full proportional lambda. So this is an example actually of where one of the practicals you're going to be doing very shortly, you're going to be using this concept to measure the speed of sound in air using water and an air column with some tuning forks. And we'll delve more into this separately. Also, what can happen is if we have an open-ended pipe, an open-ended pipe does something slightly different again. Instead of having a node at one end, we get antinodes at both ends. And so in this case, we have a proportion of half lambda in this case, and multiples thereof where we can have, so it gets a little bit more challenging. Like that. Okay, so you can have a look in your book for all of the different variations. They're all in there, but it's just nice to see that these are all stationary waves, and the circumstances in which they can be set up is different, but the fundamental concept is the same. Okay, fundamental concept is the same. The reflected wave and the original wave superposes to create our nodes and antinodes, and we get these variations depending on their situation. Okay, so in class we'll delve into these in a little bit more detail, and we'll see how many of these facts that you can remember about specifically the differences between stationary and progressive waves.